So welcome everybody. Thank you for your patience. So I'm going to start. This is the last lecture. And as I said, it's going to be self-contained, but let me just remind people what we were looking at, what dynamics we were looking at. And you will have time to ask about lectures 1 and 2 as well right now. So if you have questions, as usual, interrupt and ask me. Okay, so remember that, so actually, yeah, I want to go back to this. Today I'm starting here. Sorry. Yeah, so I want to start from here. I want to say, just to recap lecture 1. So we were looking at dynamics. So you're given a graph, an initial marked graph with initial conditions. And then we were looking at either discrete Markov chain dynamics or diffusions, okay? And the key questions were, if you're given the sequence of graphs with the vertex size going to infinity, then when do these processes x, gn, xn converge? And we answered the question by saying that if you have the marked graphs converging locally to a limiting marked graph in distribution, then of course the graph marked with the processes also converge locally in distribution. Okay, and I mentioned that the proof for the Markov chains is a simple inductive argument. For diffusions, it's a more involved coupling argument. And I didn't mention that actually for continuous time Markov chains, it turns out, which are, the sort of classical interacting particle systems like the contact process and stuff, it turns out that it's actually a little more subtle in that case. And why? Because the limit process is actually may not always be well posed under sort of generic assumptions, and you need to prove that the infinite system is well posed. But we've done that with Ankan Ganguly in an upcoming preprint. Okay, but that's this is a pretty sort of natural theorem. This is not the bulk of the main point, but this is convergence locally. The next question, which is the more subtle question, is do the global empirical measures converge? And we also answered that. For that, you need to have a slightly more refined notion of convergence of the graphs, which is a stronger version. Converges in probability in the local weak sense. Of course, you would have all these definitions in your exercises, and I've also given you some exercises to do regarding that to understand better the difference. Then you know that the graphs marked with the dynamics also converges in probability in the weak sense to the limit. And hence, the empirical measures also converge. When you have the stronger convergence probability, that's what you use to say that then the empirical measures will converge to the law of a typical party, right? And that therefore sort of mimics what you get in the mean field setting, though of course the proof is different and the reasons are different because you don't have asymptotic independence of neighboring particles. And of course you can say about graphs converge in probability in the local weak sense. And for instance, if you chase juin, NPN going to some constant value strictly between 0 and infinity, and you have IID initial conditions or a Gibbs measure to start with, then you will have this convergence. But I want to mention that, okay, this looks very much like the mean field, but we know that in fact, if you just have convergence locally in distribution, then you could still have a stochastic limit. And so this is really requires some little work, and sort of, I guess, what we try to do is to clarify the precise notion of convergence that you need to have in order to guarantee a weak limit that is actually deterministic, and saying that a whole range of limit theorems are possible in the sparse case, a broader range. And now another question is, of course, we had that when the limit is a deterministic measure, then is it always the law of the typical particle? And this we did not really talk about, but I would like you all to think about it. Do you think that that's always the case? So we know that it can be stochastic at some times, but then if it is deterministic, then indeed is it true that it will always be coincide with the law of a typical particle? And you might think, okay, maybe that's also obvious, but in fact, it depends on how you choose. It might not be, and I am not going to tell you about that now because I want to talk about something else today, but I'm just putting this as a teaser, and anybody feel free to contact me or ask me at the end, and we'll be happy to discuss it. Okay, so you could have a limit global empirical measure that's deterministic and still not have that coincide with the law of the root particle chosen uniformly. So you may want to think about why. So I wanted to emphasize that to say the subtleties that arise in the sparse case. And like I said, these are sort of the references. So as I said, this was Oliveira, Rice, and Stollerman had this result on local convergence of a different class of diffusions, though they did not prove anything regarding empirical measure convergence, though they stated a statement. And so here we've sort of done this for a broader class of processes, or a different class of processes, different diffusions, and then also continuous time Markov chains in this last bit. Okay, and also made clear the empirical measure convergence. So that's the main contribution here, the empirical measure convergence. Okay, and I would just say that for those who want to look, there are sort of related models which look at static systems on graphs, which converge locally to some limit graph and ask questions about sort of static problems. And here are some examples of people who have done that. And we will come back to that sort of later. Now, before I move on, any questions on anything that we've covered so far? Okay. Now let's really start the main part of the new part of lecture 3. And like I said, so combining the results from lecture 1 and 2, we see that if you want to understand the typical dynamics of a particle in a large graph, then you know that you can look at it as the marginal, the typical at the root of the infinite system. Okay, and then we also said that maybe you're not interested in the typical dynamics, but you're interested in the empirical measure, which is a very, very common quantity. But that then also asks you to understand what is the behavior of the root particles law, okay, in the infinite system. So this motivates to ask us the question 3, which is, can one autonomously characterize the marginal dynamics, not as a not as a marginal, but we want to give it as an autonomous characterization of a typical particle. Okay, that's what I wanted to remind you about. And we recall that local limits of random graphs are often random trees. So we will focus on this case. Okay. Okay. So I will first, when we talk about, like I said, if you think about static systems, so why is this complex? So obviously, if there was no drift, these would just be driven by independent noises. It'll be an independent product measure on a very large space. And so the marginal is trivial, right? Okay, so I'm saying a really sort of a tautology, right? But what's the problem is that all of these things are highly dependent, right? And then the question is, when you marginalize, it's much harder to marginalize. Can anyone tell me of in a static, so just, don't worry about whether there's dynamics or not, but you just have a large number of random variables indexed by a graph and you want to look at their joint distribution. Are there any other cases that you know of where you might want to understand the marginal of such a large system? And do you know of any techniques that are used for that? Anyone? I think some of these things may have been mentioned in some of the other courses. So I'll give you 30 seconds or so. Anyone? So have you thought of sort of large graphs marked by, okay, there's something in the chat, I think. Can't quite read the chat. Discrete Gaussian free field, yeah. So that's a possibility, or just any sort of Ising model, right? The Ising model on the tree, you have vertices indexed by, -1 and 1, and you want to calculate whether or what is the sort of probability of occupancy at the 0 in ZD, right? Or any general graph using one on the graph, and you want to understand what is the marginal probability. Sometimes you might not be saying the marginal, maybe the mode, but if you know the marginal, you know the mode, and you can, these are all interchangeable, okay? So, or you might want to know the limiting magnetization, which is really the magnetization is just this limiting empirical measure in some sense. And so again, you want to know what is the root particles or the origin, what's going on. So of course, we know that this is a sort of a standard thing in statistical physics, that you want to marginalize some sort of dependent, complex field. So these are graphical models also called. And so, but there, of course, we know something about the structure of the dependency, right? We have this nice, what is called a Markov random field structure, which tells you how these different variables are dependent. And then if you know a little bit about that, you know that when you're on a tree, then it's sort of easier to calculate. So let me remind people what is, so I'm going to talk about sort of what is the dependent structure first in that we have in our particle system. But first I'm going to talk about the static case. So let's talk about, just some state space S and some canonical variables YV, indexed by the graph. There's always this fixed graph underlying this. And you have some probability measure on this. And we know that it's said to be a Markov random field. So this whole joint probability distribution on configurations on this graph is said to be a Markov random field with respect to the graph if for, almost every configuration that you have, that the probability that the configuration inside a finite set conditioned on the boundary is the same as the configuration inside the set conditioned on the entire outside. Okay, so maybe some of you know this already. So this is the entire outside, but you can just restrict. So it's like a Markov property. You have this on the line where you say if you look at one, then the past is independent of the future. Okay, so of course you have lots of examples of this in the static case: product measures, Ising model, Potts model, hardcore, etc. And an equivalent formulation, which is also easy and nice to look at, of this property, is to say that it is a Markov random field if given any finite A and given any subset B, which is on the complement of A and its neighborhood, which is the closure of A, then the configuration in A is independent of B given the boundary of A, given the configuration on the boundary. Okay? Okay, so this is just Markov random field. Now it's well known, like I said, for instance, Ising models on the trees or hardcore model on the trees are easier to find out what is the probability at the node, which is really the same for those who know already these models. You don't have to know them to really understand, but for those who do know them, this will help you bridge that knowledge with this. But if you don't know about that, you can still follow what I'm saying just on its own. But the point is, if you know something about these models, you know that calculating the marginal probability is the same as somewhat calculating the normalization constant or the partition function of this Gibbs measure. And that can be done via sort of some iterations when you have this recursive conditional independence structure of the graph itself. And so that's very nice. So that's another reason to look at trees. So we are now in search, we're saying, okay, marginalization is useful if you have some sort of conditional independent structure. If it's just some arbitrary dependency, then it's really hard for me to figure out how to marginalize anything. So one question was motivated by that. We started saying, okay, in the dynamic setting, can we really unearth some Markov random field structure that's underlying the dynamics? So for now, like fix this G, and even finite or infinite, and then you have I'm going to now just remove, because we're not talking about any convergence issues of the graph changing. For us now, a graph is fixed, the initial conditions are fixed. So I will not put the superscript on Gx anymore and just call it X. And again, for simplicity, I'm just going to set the diffusion coefficient to be the identity throughout. And let's assume that the initial conditions are IID, right? So just try to understand what's happening in the simplest setting. We don't have to make these assumptions for the actual theorems, but this is for the purpose of the course. Okay, so we have this. And now the question is, if we start with IID, then at any time t, will we form a Markov random field with respect to G, right? If we do, then that's great, right? Because then we can sort of use all the machinery that we know for static Markov random fields to understand this, at least in trees. Is this question clear to everybody? Okay. So now let's, of course, I like to make things simpler and simpler so we can get some intuition. So do people think that this could be true? And it's just a question of having to prove this. So we can try to think about this in the case of, the simplest graph, like the 2 tree, right? We're looking at trees. So G is Z and A is all of this, -1, -2, -3. Okay, you can cut it off somewhere, but for now, pretend it's infinite. And then your B is 1, so it's outside, and then this is the boundary, right, of A. So of course, if A is finite, you'll have another point there, but for now, just ignore that. And so now the question is, you can take any one particular vertex in A. You have, let's just look at, you have this dynamics, and you want to understand whether the state here at some time t equals 4 is independent of the state here conditioned on this state. Do you think that that would be the case in general? Is that a new chat or? Well, my A is not just -1. My A is the entire thing, but if this is independent, I'm just looking at a subset of A. Okay, so. Right, my A is this entire thing, entire.
One question, Kavita.
Yes.
A is finite in this case?
Yeah, so I just said that for our case, I'm just assuming to make this simpler to ask, this A is actually infinite, because otherwise we have to condition on another word.
Okay.
That's what I said. I'm just pretending it's infinite for now. And let's ask if it's true for the infinite. The basic argument is not, okay, so let me help you, because we want to see what's happening at, because this is just an iteration, right? So we want to see what's happening at the previous t, let's say t equals 3. So maybe you can just take this t0 and t1 event, right? So you have all these IID if it was t equals 0, and then you want to see what happens at t equals 1. So now how many people think that you might have, if I condition on the middle node, that the neighboring two nodes will be independent in general?
Can you say again? So you are back in time?
Yeah, my question is simply, this is just to help you think. The question only relies on this level here, t equals 4. So I'm saying conditioned on the value of the 0 node, will the values of the -1 and 1 nodes be independent? You can even pretend that we're starting at 0, so all of these are IID. So the initial things was all IID, you go one step, and I'm saying if I condition on the, okay, so the answer is no, okay, and let me tell you why. So you can start with the nicest initial condition, IID, but after one stage, you're not going to have the preservation of even this Markov random field property, even though you think you might, because the dynamics are sort of local. So maybe there's sort of some localization. That's what you would hope. Why is that the case? Let's try to get some intuition why this fails. Because if you condition on this, it tells you something about this particle, right? This state, the value of this state. But the evolution of these two also depended on the value of this. So this and this also depend on the value of this state, right? So remember that the value of this depends on this neighborhood, this -2, as well as some external noise. So this purple depends on -2, -1, 0, and some independent noise. The green depends on 0, 1, 2, and some independent noise. So both of them depend on 0, and you've conditioned on the 0, so you're sort of correlating them. Okay, so it's not hard to see, especially in the Markov chain case, that it's not going to hold. So our great idea of trying to reduce this to the static case and say at every time t, you're going to have this Markov property is not going to work. Okay, so what might we do? Is there another question in chat? Wait, let's see. Yes, so very good. So someone, Lior, yeah, exactly. Thank you very much for the question. I'm glad I checked it. Wait, how do I get rid of this chat window? Okay, yes. So in fact, why not, the problem here was that, okay, because this thing is correlating these two. So why not condition on that as well? So condition on histories, that was the idea. Very good. So let's look at, let's condition on the particle histories and then see. So remember my bracket T is going to be the history. So let's try to do that, and let's reformulate and say now how the histories form a Markov random field. So again, we can look on what happens at G, and now I'm conditioning on both of these, and in fact, the entire past. So I'm not, couldn't draw that. And now I want to see again if purple is independent of green, given the entire red column here. So of course, you want to see the entire history, but in particular, we would want the value at -1 at t equals 4 and this at 1 at t equals 4 to be independent, conditional in this entire past. We need more, actually, if we're asking histories to be a Markov random field, but in particular, this should be true. So do we believe this would be true? So we might think, well, okay, the evolution of all of these depend on this only through these values. So if we're given all these values, sort of we're decoupling these two dynamics, right? So we should get, I mean, you have to actually prove it, but otherwise it seems like maybe that would be true. Okay. But there's a subtlety, okay? And that's actually not true. So you just by conditioning this, it doesn't mean when you condition on this, the dynamics over here is not simply the dynamics of these plugging in the values of these, because this conditioning changes how the noise interacts. And so you have to think about why it is not. And I have, one of the good exercise will be to try to construct a counterexample yourself. Okay. And
just one question. So when you conditioning on the past of 0, you are kind of fixing the noise of 0, and this affects the neighbors.
Yes, so I'm saying something about the noise, right? The noise process and the noise process over here, because the neighbors depend on the evolution of this. So, I mean, the noise process here is independent of the noise processes here. That's not the point, right? So the noise processes here are independent of the noise that drive here and noise that drive here, right? Because we have the psi all independent.
But
what correlates is the two noises of the other two. Because, okay, why is the problem? Why? So we're going into, rather than letting you think about it, I guess we're going into the explanation, saying that the reason is because it correlates the dynamics that from here to here. When I condition on this, we know something about this, right? Because given this, it's not just that you have this dependent on this. So -1 at time t equals 4 depends on the past 0 at time t equals 3. But you also know that this 0 depends on sort of the past at -1. So, and also of past of 1. So giving this also gives you some information about the pasts of the neighbors, and that creates a correlation between the two. Okay, so you have to actually, I cannot sort of do the proof here, or it's something that you should think about. And we have actually given lots of examples in our paper, okay, to explain this. But it's really, first I thought, okay, this must be true because it's local. And so at this point, we were going to throw our hands up. Okay, there's maybe no nice structure in this dynamics. But then I thought about this a little bit more, understanding what correlation is going on. And so then we said, okay, I'm just going to define to you what is called the double boundary, which is simply just the boundary of the boundary, not including the set itself, and as union the boundaries also. So just two distance to outside the set. And now we can call this a second order Markov random field. If you condition on the double boundary, what's inside is independent of the outside. So another way to think of it is it's a Markov random field on the square graph. Okay. So now the question is, are the histories independent conditioned on the double boundary? Okay. And that's yes, it turns out that that's true. And so in particular for all A finite and B in the complement of A union its double boundary, then you do have this Markov random field property. Okay. And if I had a longer course, I would give you a full proof of this, or at least in the Markov chain setting, which is easier, and also give you more intuition on this. But then I won't be able to get to the other things. But the idea here is just goes back to what I said here, that if it's only correlating the two neighbors here. So if you condition on this as well, this only correlates this, and this correlates this and this. So if you condition on two of them, this and this does not get correlated. Okay, so that's about all I'm going to say in a line. But I have given you, so if you've all the diligent ones who have already completed the exercise I've given, then given the two lemmas that I asked you to prove and the dynamics, you will be able to prove this a little bit more. Okay, and with a little bit of thought. Okay, but in fact, as you saw that, in my diagram, I was sort of conditioning on A, which is infinite, because it turns out that's what I need in my application. And so we had to prove something stronger, not that just that this is a second order Markov random field, but what we call a second order sort of semi-global Markov random field, in the sense that we have to allow A to be infinite. And we can also allow the initial conditions not to just be IID, but it can be any second order Markov random field. So we have this sort of propagation that if you start with initial conditions, second order Markov random field, that at any time under this dynamics, the histories also form a second order Markov random field. Okay, and we can allow A to be infinite, which is crucial. And I have another exercise for you all to all think about what happens. I mean, whenever you have a Markov random field, can you always make this A infinite or not? The answer is no. And the question is, come up and think about why and think about counterexamples. Okay, so it's just to say that it's a non-trivial extension to go through the infinite case, and it's not obvious that it will hold. Okay. Yeah, because, in many things we say, oh, if it holds for finite dimensional things, and we can just sort of extend it and get it for all infinite. But here you have to be a bit more careful. Any questions on this property? Because this is going to be used. Is at least the property clear? If not, obviously the proof may not be completely transparent yet. But I'll give you some idea on the proof. Okay.
There are a couple of people asking about the definition of a double boundary.
Oh, okay. Sorry. Let's see that. Thank you very much. Okay, the definition of the double boundary is simply the boundary on a graph in which you connect all vertices that are distance 2 in the original graph. So that's one way to think about it very simply. The other way is just say you take the boundary. I'm going back to that picture. You take the boundary, you take its boundary, and then don't consider the set. And you take the union of the boundary and the boundary of the boundary, not containing and not including the set, and that you get a double boundary. Just all vertices that are distance 2 or less from the set. Graph distance 2. Is that clear? Okay.
I just have a curiosity question. Here we have dependence in one step in time. So I guess if we have a dependence in 2 steps, we just have to go further in the boundaries, maybe, to get the same result. It's not working.
As I've told you before, that if you can always, the underlying interaction graph is not fixed, right? It's you have to choose. So you have some n particles, and then you create the graph based on the dependencies. And then this is always true, right?
Yeah, so the step in time doesn't matter.
Yeah, I mean, the number of steps, you'll just change the graph structure such that anything that is influencing its one-step dynamics is a neighbor in the graph. So
yes.
So in a sense, what you said is correct, but you don't need another theorem. It's the same theorem with with the graph that is actually capturing the dependencies.
Yeah, so I just have to modify slightly the graph. Okay, thank you.
Yes. I think Julia asked this question also, but it's good to get it clarified.
Okay, thanks.
Thank you. Okay, great. Okay, so we can allow more general initial conditions as well. And just wanted to say, so after we did this, we were doing this sort of understanding of the structure is there for Markov random fields and then diffusions. And then we just saw that, it was sort of bedded. It was not written in terms of Markov random fields, and they were not really looking at the order. We really care about the order for reasons I will tell you. But there's some prior work on when only in the case for graph, which is a ZD, for surprisingly all the way back. So for gradient diffusions, and somewhere within that paper, it really says that there is this very nice paper of Deutschel and then follow up, who looked at only bounded drifts, and Catiot-Roelli and Zassin, who looked at sort of unbounded drifts. So this is for gradient diffusions on ZD. But they very much use the gradient structure there very strongly, as a remark in those papers say. So, but we don't assume any gradient. And then more recent work looked something at non-gradient processes on ZD, but they have to have shift invariant initial conditions. So it's only something that works sort of on lattices. So I will tell you a little bit about our proof, which sort of is using a slightly different approach and works for general graphs and also non-Markov processes. And it's also just to those who know about this, these kind of questions are relevant to questions people are interested in study of Gibbs, non-Gibbs transitions. That is, if you start with the Gibbs measure and you evolve, then when do you lose the Gibbsian structure? So this has some relation to those kind of things. But let me get back to the proof. As I already told you, in the Markov chain setting, you have to exploit some general conditional independence relations. So the real idea here is to actually have figured out that what is the correct conditional independence structure that you want, which is then to prove it, you can do it with some work, and I've left it as sort of an exercise, and then use the dynamics to extract appropriate functional relations. So I should say that when I first saw, okay, I think the double boundary is going to be sort of have a Markov random field, not everybody who was working with sort of we didn't necessarily believe it would be true, but it does turn out to be true. So you combine to get the proof. Okay, but what about in the diffusion setting? So we can't do it by hand, obviously, because you have this, you don't have this recursive structure. And so the diffusion setting invokes the, Hammersley-Clifford theorem. Let me just remind you, for those who don't know what it is, it's a way of characterizing Markov random fields on finite graphs. So suppose you have a finite graph, and the clique of a graph, remember, is just a subset in which the induced subgraph on V is complete. So a subset where every vertex is connected to each other. And I'll let CLG denote the set of cliques of the graph. Then some function on the configuration space R plus is said to be a factor on this finite graph if there exists functions associated with each clique in the graph, such that fx can be written as a product of these functions on the configuration on those cliques. Okay, so this is not the theorem, this is just a statement of what it means to factor. And the Gibbs-Markov or the Hammersley-Clifford theorem tells you that if you have a finite graph, and for now just assume S is a discrete state space for simplicity of formulation, then if the probability mass function on the discrete set factors on G or equally admits this representation, where this is some normalization constant C, then in fact, this probability mass function defines a Markov random field with respect to that G. Okay, any questions on this? So maybe some of you have seen this before. So this is a very classical theorem. If you know Markov random fields, probably the first thing, or graphical models, first thing you're going to learn. Okay, so it's a very nice theorem with a very nice proof, especially the converse. So yeah, you also have a partial converse. If this probability mass function is strictly positive, then you have the converse. So it's a really quite a tight characterization for strictly positive Markov random fields on finite graphs. Okay. And of course, we have second order Markov random fields. It's an immediate extension. Like I said, instead of taking G, take the square of G, and then it's a Markov random field with respect to that. So you immediately have the two cliques, which I'm calling all those whose not just neighbors, but is the induced subgraph that has diameter less than or equal to 2 is fully connected. Okay, so you have just a corresponding factorization theorem for cliques, for second order Markov random fields as well, quite trivially. Okay. So what do you do with that? So in the diffusion case, so for any finite graph, you can use Gersanov's theorem. And so, of course, here we were talking about the probability mass function on a discrete set. So you have a similar thing where if you say that if you have some sort of product measure and you have the density of your process factorizing in this way, then you have the same thing for a continuous state space. I just wanted to do this because it's easier to state. So we use, of course, the continuous version for the diffusion, and you use Gersanov's theorem, which is a theorem that relates the measure of this SDE with respect to the measure without the drift, which is now just, in this case, because sigma equals 1, is just product Wiener measure. And then we show that that factorizes in the right way. And so we invoke this Hammersley-Clifford theorem to conclude that it has a second order Markov random property. I mean, I gave you another intuitive explanation as well, but this does this by just using this factorization theorem. But going from finite graphs to infinite graphs is considerably more complicated. And so you have to use a much more subtle approximation for infinite graphs. So there was a question by Omar about how do those papers that I mentioned earlier use a ZD structure. So the first set of papers, which actually do gradient diffusions, they not only use the ZD structure, but they use the gradient structure a lot, and they're using Malyavin calculus, and they're not using this theorem at all. So those theorems are not using ZD as strongly, but they're using the gradient structure a lot, and they're using some Dobryshin contraction argument to get some idea of what they want. But the de Roger-Royle paper is strongly using ZD because they assume that you have a specific entropy, which means you have to have some sort of lattice structure, and they're using the shift invariance in order to do the calculation and understand this. So I hope that answers your question, Omar. Okay. Okay, so okay, so now the thing is, so how to go from finite graphs to infinite graphs, that's where they use this sort of, so we use sort of a completely different argument, which involves sort of understanding projections of Markov random fields and whether that's preserved. I gave a little exercise on that. So doing the exercises before you read our paper might help you understand some of the subtleties. And then we have to show this, that it tights and it converges. So we do that. Okay. And it turns out that this ends up being more complicated for jump processes and with other initial conditions, which I will not get into right now because that's not the focus of this course. But I will just mention that will be coming up in an upcoming paper with my student, Ankan Ganguly. Okay, any questions on the conditional independent structure before we say, okay, why did we do this? Okay, it might be, of curiosity in itself. It's something interesting in stochastic analysis that you can characterize infinite dimensional SDEs as Markov random fields for sure, which was the motivation of these other people. But, what can we do with it? Okay, and like I said, in there, they didn't really specify second order or first order. They just wanted to see if it's some Gibbs measure, which has some finite. Okay, so we want to use this for the derivation of the marginal dynamics. And today I'm trying to, as much as possible, keep it in the Markov chain setting so that more people can follow, even if you don't know stochastic analysis. And I will mention more on the diffusion depending on time. Okay, so now we have the structure and we have this conditional independence property, how can it be used? Clear? So what did we really want to do? Just reminding you, we're looking at only when the limiting graph is an infinite D regular tree, like D equals 3 or D equals 4, etc. For today, I mean, we obviously want to look at the case of Galton-Watson trees, but since I just have one lecture, we will look today not only just at D equals D regular tree, I'm going to look at just the line. Okay, so TK is just, we look at infinite K regular tree, K equals 2, that just gives you a diffusion on the line. And remember that theorem 1 tells us that this X row and its neighborhood can be obtained as the marginal of the infinite coupled system of Markov chains, right, with V in this. And so what we want to do is we want to understand the marginal X row. And I'm going to always set rho to be 0 because we can always identify the 2 tree with Z. And we're interested, actually we said we're only interested in X0, but it turns out that the right thing to be interested in over here is not just the autonomous dynamics of X0, but X0 and its neighborhood, okay? Which is fine because in the sparse case, if you take the root and its neighborhood, it's still some finite set. So you have this infinite dynamics, and I'm saying to understand to marginal, I just have to understand a finite dynamics, irrespective of how large this n is, right? So it's a huge dimension reduction in any case. So what we want to do is we want to look at 0 in its neighborhood and see if we can characterize the law of this without referring to the infinite dimensional system. Just the description should not refer to the infinite dimensional. We don't want to say it's a marginal of the infinite dimensional system. Okay, that's our goal. Okay. And how can we exploit the conditional independence structure? So again, I'm going to write this like this. And now what we're going to do, so this is my die, and these black vertices are the ones I'm interested in. And remember, this is the dynamics. Now I've replaced the V's by I's. And I am, remember, xi t plus 1 will depend on xi t as well as 2 neighbors, right? The pair, it's 2 neighbors, unordered pair, and then external noises. Okay, so I'm just rewriting the dynamics in this special case. And now what we're going to do, we're going to generate another stochastic process, y minus 1, 0, 1, that has the same law as this marginal process, but whose evolution depends only on its own history of its own state and the law of the history of the state, or equivalently, the law of the marginal process, right? Because I'm saying it has the same law. Okay, that's what we're going to try to do. Right? So because I want to find, what do I mean by an autonomous characterization? This xi is defined as the marginal of this infinite system, right? But I am going to find another set of y1 minus 1 with the same law, which has an autonomous description just in terms of its own histories. Is that clear? Okay, let's, if it's not, it should become clear as we go along. Okay, so now let's see, what is the evolution of the middle particle? Okay, so that's really going to be simple. So this should just be y1 of t subscript here. So note that the evolution of the law of the middle particle only depends on the states of the neighboring particles, which, I'm sort of allowing in my dynamics. So it would just remain the same as before, right? So y0 t plus 1 is f of y0 t, then y minus 1 t y1 t, and then psi 0 at t plus 1. Clear? There's nothing. So the problem comes in really understanding the evolution of, let's say, minus 1. Because minus 1 will depend on both 0 and minus 2, but I'm not allowed to refer to minus 2. Is this clear? Because otherwise it's not autonomous, because then minus 2 will depend on minus 3, and then I go back to marginalizing from the original system. So how can I do that? So remember now the x minus 1 at the next time will depend, of course, at x minus 1 at time t, which is fine. And then it will depend on the joint law of minus 2 and minus 1, and also 0. But 0 I know, so let me just ignore 0 for now, okay? So it depends on the joint law of minus 2 and minus 1. But there's symmetry in this system. The joint law of minus 2, minus 1, 0, 1, I need this, right? This whole joint law in order to define what's going on next. And that cannot be obtained just from the y minus 1, 0, 1 dynamics a priori. So I have to use something. And the point is that if I have access, of course, I have all access to the states of 0, because it's my y states, I have access to them. So I have all access to states minus 1, 0, 1. So if I condition on 0 and 1, remember that the past of this is independent of the, so, right? So I'm trying to understand the evolution of minus 1. So we assume we have access to the states in the law of y minus 1, 0, 1. It suffices to know the conditional law of y minus 2t given the past of minus 1, 0, 1. Is that clear?
Can you say again? So
sure.
Right now you know the state of 0?
Yeah, so we're trying to evolve this Markov chain. We know all the states, but only of y1, minus 1, 0, and 1 up to time t.
Okay.
Right? And now we know that because that's we're evolving our system. But now I want to evolve it at t plus 1. I need to now decide how to evolve it, right? Evolve the law of the process. That in a way it's consistent with the evolution of the law of xt, but I cannot refer to the values outside minus 1, 0, and 1. So
yeah.
What are we going to do? In the original system, in order to know the value of y minus 1 at time t plus 1, I need to know the value of y minus 1 at time t, y0 at time t, those are fine. But I also need to know the law of y minus 2,
yeah,
given all the past of minus 1, 0, 1.
Yeah.
Right? Because I know the past, so I can say at least I need to know the law of y minus 1, 2t, but it's okay if I know only the conditional law of minus 2 given the past, because I have this information. Okay. Clear? Okay. I don't expect you to necessarily, follow everything in one go, but hopefully I will say enough details that you will be able to see. But the second order Markov random field property says the conditional the conditional distribution of minus 1, minus 2t at time t, conditioned on the past of minus 1, 0, and 1, is the same as the conditional law of minus 2 given just minus 1 and 0. Because when I condition on the double boundary, then this 1 becomes independent of minus 2. Okay? So you may have to think through this. But the point is that's where the condition. So, okay, how does that still help me? I still have to know the conditional law of minus 2 given the paths of minus 1 and 0. That's still outside my 1, 0, 1 system. So what can we do?
Can we replace minus 2 by plus 1?
Yeah, so we can just shift everything. Everything is symmetric. So the law of minus 2 given the past of minus 1, 0, and 1 is the same as the law of minus 1 given the pasts of 0 and 1. And that only depends on something that's the law of the process up to time t. Okay? So we've used symmetry properties and we've used the conditional Markov random field property. and the form of the dynamics to conclude this. Okay. Okay. So, okay. So, oh, there's a problem here. Okay. So once you know this, you can write down, I will put another screen up in a minute, but this is giving me some problem. Okay. So once you know this, you have an autonomous way to generate this. So let me say what the algorithm is. You first, let's say you have somehow generated the first up to 3 steps, let's say, of this process, right? You've generated the law of this process. Or you can generate it. Let's say you could do it up to time 3. I just have to tell you how you do it at time 4. So what will I do? To evolve the 0 process, I will just look at the values at -1, 1, add some external noise, and then put it through this function. Yes, so that's easy. Now to do -1, I have to look at the law of this -1 given 0 and 1. So I have to first calculate that given the entire past of that. Then I apply that law conditioned not at, I have to evaluate it at the paths of -1 and 0, not at the paths of 0 and 1, right? Because we're doing the shift. And that gives me the conditional distribution of -2 given these paths. I use that to evolve the process -1. And you can do a similar thing by flipping for 1. Okay? Okay. So the point is that there's a discrete time algorithm which allows you to evolve this process completely looking at only -1, 0, 1 in its history and to get a null. So this turns out to be, this transition kernel is dependent on the law of the process. So it's actually a nonlinear process again, but it's now a non-Markovian nonlinear process because it depends on the law of the entire history. Okay, and this is, it's easier to explain what is going on in the Markov chain setting, but it's actually more cumbersome to write it. So I'm going to, for some reason, this is frozen. So if you give me a second, I will just bring up another slide, which will tell you what the form looks like for the diffusion setting. Okay. So in the meanwhile, you can ask questions while I'm doing this. So any questions? Does anybody understand what this algorithm is doing? Or do you want to see the algorithm exactly? I think you just have to understand what is the spirit of the algorithm and not really all the details. So let me just bring this up. Give me a second. So now let me tell you what happens in the diffusion case, which requires considerable more work, just a second. Okay. Sorry for that. Okay, there's a question here. So this depends on the homogeneity of the tree. Yes, certainly we're using symmetry properties. Without any symmetry properties, you're not going to be able to say anything. So suppose you had a completely inhomogeneous sort of system, then you cannot clearly say anything about a typical particle. There's no notion of a typical particle, right? So unless you have some homogeneity, then you don't have. But I'm going to tell you a little bit about the random case. I don't need this only for deregular trees. I'm just showing you the proof for that. So, okay, let me share the screen again. Full view. Okay, just to quickly tell you again, suppose you had, the diffusion case, right? And you had it like this. Now, x minus 101 is what you want. And now I've just put them as superscripts to just keep the t sort of more compact. It turns out that you have to use something called a projection lemma. I'm not going to go through all these details for the diffusion. I will just tell you what the final form looks like. But you use the same idea of symmetry plus this projection theorem plus some other things to get the following characterization. So remember that the original system was dxit is half. And I'm doing the special case when the drift is just an average of the two interactions because it's easier to explain in that case. So this is the original system where you have a sort of linear drift, the drift with the local empirical measure. In this case, it's just half x1, x0 and then half b of x1, x2. Okay, is this clear? And then that's the drift, and then you have, of course, some Brownian noise. And now I define this gamma t to be the law of x1 at time t conditioned on the pasts of 0 and -1. Is this clear? Of the histories of 0 and -1. Okay, so what is gamma t? It's just x0, small x0 and x -1 are functions, on C0t. And I can write this gamma t to be the law of x1. So it's a function of x0 and x -1. So is that clear to everybody? Okay. And now I'm saying that I have my x -1, x0, x1 is equal in distribution to this particle process y -1, y0, y1, where we can just look at the dynamics for y1. The dynamics for y -1 is sort of symmetric. So of course, where it involves the term with y0, you don't do any change. But where you have the evolution in terms of what would be the outside particle y2, you have to do an integration with this conditional law evaluated not at x0, x -1, but at y1, y0. Okay, so you just have to understand the form, not all the details. Okay, so what you get is really now a non-Markovian system that shows exactly how it is, where because the evolution now depends on the entire trajectories y1 and y0 up to time t. Right? But that's all you need to know. So, but gamma t, we said is, you might say, gamma t involves the law of x1, and we're trying to make this autonomous. But I've told you that the law of x -1, x0, x1 is the same as the law of y -1, y0, y1. So I could have just as well put this as the law of y1 given y0, y-1. So this is completely autonomous in terms of gamma t only depends on the law of the process up to time t. And so now you're getting this sort of, again, a non-Markov process, but a non-Markov nonlinear process. So it's again like a nonlinear process, but on trajectories. Okay, and I only told you, and that's all I have time for. I mean, this would take several more lectures in order to give you all the details, but maybe I will tell you some things because we started late. So I would like to say that I only showed you that through all my conditional independence and symmetric arguments, I said that if I take the infinite system and I look at its marginal distribution, it should satisfy this equation. Right? Are people somewhat convinced that that is the case? Can you give me some nods or this nods or nods? That it seems, okay, plausible that the marginal will satisfy some sort of nonlinear equation like this, right? In the Markov chain, it's a discrete evolution.
Kavita, excuse me, I just have a quick question.
Sure.
This is true only for finite system, no? Because the double boundary was true only for finite graph. That's what you said, no?
No, the proof I said that I used the Hammersley-Clifford for finite graphs, and then we extend it to infinite graphs using a somewhat complicated argument.
So it's true for infinite graph too?
Yeah, of course.
Okay, sorry. Okay, thank you.
True. Okay,
Kavita,
graphs and infinite A. Yes, please ask.
Can you comment about the relation with the MacLean-Vlasov?
Yes, thank you. This is the perfect slide to ask that question. And so what is gamma t? Gamma t is simply the law of, I'm replacing x1 by y1 here. I can do that because of this, the fact that x -1, x0, x1 is equal in law to y -1, y0, y1. This gamma t is also equal to the law of y1 of t given y0 t is equal to some small x0 t, y -1 of t is equal to small x -1 of t, passed. Okay? So if you look at this process, you have trajectories. So this term, which is the drift, so of course the diffusion is some diffusion. This term in the drift, what does it depend on? It depends on the law of the process, y, and the past trajectories of y. So it's nonlinear because its evolution, its drift depends on the law of the process. So you can write this as an integral, right? This is bracket, by the way, is just as usual. This is a random measure. This gamma t, y1, y0. I don't know if you are able to see my highlights, but I hope so. Okay, thank you. Yeah, so my highlights, this measure is a random measure which depends on the paths of y1 and y0 up to time t, and it's exactly this random measure. And I integrate my drift b, y1t, this other variable, with respect to this random measure. So it's a sort of complicated conditional. So it's a McKean-Vlasov where the dependence on the law is coming through a conditional expectation on the law. I hope that helps. And it's also, it's a path-dependent McKean-Vlasov with conditional independence there. So you can think of it as a nonlinear McKean-Vlasov on the space of trajectories. Okay, but I don't formulate it.
Can I make one more question?
No.
For the complete graph, we have this kind of heuristics that you should trust to derive the equation of the limit.
Sorry, what did you say in the heuristic?
In the complete graph case, you showed us in the first lecture heuristics to derive the equation of the limit.
Yes.
Here, it's possible to have some heuristics to derive the expression.
I mean, what I have done is a heuristic because I've not.
Okay.
Right. I mean, I told you that once you understand this conditional independent structure and you use the symmetries, then you can write this down, right? Like, so in that sense.
Okay. I see.
Yeah. I don't have a. Okay. So just wanted to mention a couple of things maybe. So all I said is that this that this equation characterizes the marginal. Of course, if you're, in stochastic analysis, you have to ask, is it the unique solution, or can this equation have multiple solutions, right? So even if the original system, so we can that actually takes work. And so you can prove that there is a unique, so, you can just ignore the fact, you can completely ignore all of this and just now look at only this question. I'm given some equation driven by some independent Brownian motions. Can I find a solution of this form where gamma t is just in terms of the law of y's, right? So you can ask this, it's an SDE question. And of course, we have existence through this limiting argument, but do you have uniqueness? And in fact, you can show under our conditions that you have uniqueness, and that's, again, outside the scope of a, one lecture to explain. But I would like to say that this is actually a non-trivial proof, and we have like several different types of proofs that we can do for uniqueness. So let me just summarize that. And this actually also gave, I think whoever asked me about the nonlinear, maybe Guilherme, that, for mean field dynamics, we saw that the dense sequences, that the limiting dynamics of a typical particle is given in terms of some B, cap B, xt driven by the law of the xt. And here this gamma t is driven by the law of yt, but now it depends on the paths as well. So maybe this is a nice way to see the connection. Okay, so the only thing that I haven't written is gamma t is not just the law, but yeah, it is. I mean, I could have written this as some functional of the law, but I've written it more explicitly as sort of an integral with respect to a conditional probability of the law. Okay, but it has many unique features that don't come up in regular mean field systems. But at least you see that this is an analog for sparse graphs of what one has for mean field systems. And maybe the last 1 minute, I will simply say that you can generalize this to autonomous deregular trees. We did it just for D2. Of course, you will use more symmetry properties of the deregular, but it maybe would not, we would really like to extend this to unimodular Galton-Watson trees, right? Because most limits come as unimodular Galton-Watson. And so it turns out that we can do all of that. And so that will require another 2 lectures or 3 lectures. But essentially, first you have to think of getting a conditional independence property like of the sort I said, but now it's annealed over the randomness of the graph structure. And so it's more complicated and uses unimodularity, which I can't get into right now. So maybe I will just conclude with, if you remember that if you look at the discrete time contact process and you look at the mean field approximation, it's going to be red. And now I do this, this algorithm that I said to evolve the process. And in fact, I actually do an approximation of the algorithm to make it run faster. And the blue over here is actually the full it's on a cycle graph, by the way. And the green is the simulation, and the blue is the simulation, and the green is this local dynamics that we did this algorithm. And so you can see that the approximation, as the theorem proves, is a better one than the mean field. And so here's an alternative. There are, of course, some negatives because it's non-Markovian, so it's a more complicated evolution than a nice mean field. But the point is that the system is evolving in a non-Markovian fashion. So if you want an autonomous evolution, you're not going to get something really simple. So you can, that's my summary. So in summary, the course, I hope I've given you some idea of how you can characterize local or marginal dynamics of large sparse networks, providing an alternative to mean field approximations as long as they look sort of asymptotically tree-like in some sense. And there are many, many interesting other questions. So maybe I should stop here to not go too much over. Thank you.
Thank you. So we can all unmute to thank Kavita for a series of lectures.